Okay, so we stopped here on the straw and label wave question. So number 7. So if you were to have to do this, draw just kind of a wave and then just know that there's sort of this middle line right here. This is the equilibrium. Okay? And so from the equilibrium to the tallest point or the lowest point, either way, this would be known as the amplitude. And then the top part of the wave is known as the crest. And the bottom part of a wave is known as a trough. And if you went from one peak, so I'm going to go from one trough to another trough, this would be a wave length. This would be a full back and forth motion. Okay? So that is the wave labeled. All right, number 8 says, how much time will elapse between hearing and seeing an event that is 600 meters away from you? All right, so we are going to assume that the temperature is 20 degrees Celsius. All right, and this is going to be one of those that we have to use this velocity equation. Okay, because this is wanting us to figure out how much time, and if we find out velocity and we know distance, remember velocity is equal to distance divided by time. So we could rearrange that and solve for time. But first we have to find out the velocity. So if you would have to look on a table here that gives you the initial temperatures, the initial velocities at certain temperatures. So if you were to look on that table at 20 degrees Celsius, it would tell you that the initial velocity is 331 meters per second. And that the temperature is 20 degrees. So if you go through that and calculate, you would get 343 meters per second. And then if you rearrange this equation and solve for time, time is equal to distance divided by velocity. So 600 meters divided by 343 meters per second should give you around 1.75 seconds. Okay. All right, number 9. This one is very similar, except for it is wanting us to find distance. It wants us to find feet. So if it's wanting us to find feet, then we're going to need to use the other part of that table that has feet per second. So if you want to pause the video really quick and go to, let me find what table that is really quick. If you want to go to your textbook and look at, I have a data sheet here somewhere. Look at data table 5.1. 5.1 will show you what I'm talking about as far as the velocities in meters per second or feet per second. So in this one, we're going to do the feet per second one. Okay, so again, we're going to be using this equation, but instead of finding time, we're going to find distance. So distance is velocity times time. So same exact equation, only instead of this 0.6 number, it's a 2 feet per second over degrees Celsius times the present temperature. So our initial velocity, and if you go to the table, it tells you like at 50 degrees. So for that, the initial temperature at 0 degrees is 1,087. So 1,087 feet per second plus this 2 feet per second divided by degrees Celsius, and you have to multiply that number by whatever the temperature is. So it's 50 degrees Celsius. Anyway, so you're multiplying 50 by 2, and then you're adding the 1,087 number. So that'll give you 1,187 feet per second. And then if you take that number and plug it in for this velocity here, so 1,187 feet per second times the time here, so this 1.75 seconds, then you should get this 2,077 feet. But that's not the answer, because this says that an echo bounces off. So if it's an echo, that means that it's traveled one distance and back to you. So all you have to do for this one, if it ever says anything about an echo, then you'll have to divide by 2. So it's really 1,038 feet. Or as far as this one is concerned, because of that 50 degrees without a decimal, let's just make it 1,000 feet. Okay? Okay. Number 10. Number 10 says that a mass on a spring oscillates 25 times in 5 seconds. It has a wavelength of 1.25 centimeters, and it wants to know what the velocity is. Okay. Didn't give you very much new space here for this, did I? So this goes back to our velocity is equal to wavelength times frequency. It gives us wavelength. It wants us to find velocity. So what are we going to have to find? We're going to have to find frequency. Okay, so if we do frequency is oscillations per time. So let me get my calculator really quick here. So we've got 25 divided by 5, which is 5 hertz. So 25 oscillations divided by 5 seconds. Let me make that a little bit, whoops, a little bit bigger. So our frequency becomes 5 hertz. And then we just got to plug this in. Now, as far as the wavelength is concerned, it's given as centimeters. So I would suggest you convert that to meters. And then multiply that by 5 hertz. So let's see what that should be. Okay, I got 0.0625 meters per second. And as far as significant figures are concerned, these two are just two significant figures, so 0.063. Okay. And we've got one more here as far as chapter 5 is concerned. It says, how long will it take to hear thunder if lightning strikes 4 miles, which it gives the amount in feet as well. Actually, it doesn't give the amount in feet, because that's weird that I wrote that. 1 mile is equal to 5,280 feet, and this is 4 miles, so we've got to convert that over. And it says that the air temperature is 80 degrees Celsius. So if it's telling you feet, then you can use that velocity one that has the feet per second instead of the meters per second. Okay, and again, this is wanting us to find how long, so that's how much time. So velocity is distance divided by time. If we rearrange that, time is equal to distance divided by velocity. So first, we've got to convert this 4 miles over into feet. So 4 miles For every 1 mile, there's 5,280 feet. I don't know why I wrote it like that. That was confusing. So that's 21,120 feet is the total distance. And then for the velocity, you do that 1,087 feet per second number again, plus 2 feet per second, and then whatever the temperature is. So that's at 80 degrees. Okay, so if you take 2 times 80 plus 1,087, you should get 1,247 feet per second. Okay, so now you just take your 21,120 feet divided by this 1,247 feet per second. So distance is your feet versus velocity. So you end up with 17? Is that it? 120 divided by 1,247 is, 17 seconds. It's like 16.9 something whenever you put it all in. So because of the 4.0 number, that's 2 significant figures. So go ahead and just make it 17. All right, so as I mentioned on Friday, I'm not going to do any on here for the electricity. As far as electricity practice is concerned, you just look at that paper that we finished up on Friday. All right, but what I'm going to give you here is just some equations. Obviously, you don't have to memorize these, but just want you to be able to recognize them. So one of them was if we were ever going to have to find like the amount of electrons, we used this number. And remember that the charge of an electron or proton, both, is this 1.6 times 10 to the negative 19 coulombs number. Another equation that we did was force for electricity, electrostatic force. So you had this Coulomb's constant, which is K times Q1, Q2 over R squared. Or sorry, in your book it's distance squared. And so K was 9 times 10 to the 9th Newton meter squared per Coulomb squared. We also had an equation for electric potential, which is V. And on the next page, I have a table that kind of shows you what all of this is. So this was work divided by charge. We had an equation for current, which was I equals charge divided by time. We also had Ohm's law, which was voltage or electric potential is equal to current times resistance. We had an equation for cost, so watts times time times the rate divided by 1,000 watts per kilowatt. And then if it was resistance as a series, we had R1 plus R2 plus R3, and that was it. For parallel, it was like 1 over R is equal to 1 over however many you have in that situation. But just remember that you have to solve for R total. This is total, by the way. So when you go through and do 1 over on all of these, you have to remember that this is in the denominator. So you end up having to do 1 over whatever your answer is. We did an example like that on one of those practice papers. And then we also had power was equal to current times voltage. Okay, and then, like I said, we have this table here too. So I'll zoom in a little bit so that I can write a little bit bigger. So for heat, the symbol for heat is Q. And remember that heat is measured in calories, and it could also be kilocalories. Okay. Specific heat, the symbol was like a lowercase c, and the unit was calories per gram degrees Celsius, or kilocalories per kilogram degrees Celsius. Work has the symbols W, kinetic energy, and potential energy are all considered work, and the unit for those are joules. And more specifically, kilograms times meters squared per second squared. Frequency has the symbol F, lowercase f. It's measured in hertz. A hertz is a 1/2. Wavelength has this funny looking hat symbol, and it is a length, so it's measured in meters. Period has an uppercase T symbol, and it is measured in seconds. Charge is a lowercase q, so we have a uppercase Q for heat, but a lowercase q for charge, and it is measured in coulombs. Electrons, its symbol is just like a lowercase e, and it's also measured in coulombs. Electrostatic force is just an F with a little e subscript, and since it's a force, it is measured as a Newton. And a Newton is a kilogram times meter per second squared. Electric potential is a V, and it's measured in volts. So its symbol and unit are both the same thing. And a volt is a joule per coulomb. Electric current is an I, and it's measured in amps. And an amp is a coulomb per second. Power is still a P like it was back in chapter 3. And power is measured in watts, which is a joule per second. Resistance is just an R, and it has a funny looking hat symbol, which is an ohm. It's a volt per amp. All right, so that is the end of this review. If you guys have any questions, don't hesitate to ask.